Hello, this is Jeff Badge of the Grinding Doc, and this is a short video on resonance, or more specifically, resonance when you are dealing with chatter issues. And chatter is a big term, complicated term, means lots of things, but we don't want things to vibrate at their natural frequencies. Or let's put it, no, they're always going to vibrate at their natural frequencies. Let's be more specific. We don't want to excite the system at its natural frequency. We're going to excite it, we can't avoid it, but we don't want to excite that system at its natural frequency. And that goes for chatter, and I'll talk about what that means in a minute. So let's take a look at Joe the Grinder. And Joe the Grinder is pushing his granddaughter on the swing. And his granddaughter goes back and forth and back and forth and back and forth. And she makes one back and forth motion every 4 seconds. So the period is 4 seconds. The frequency is 1 divided by 4 is 0.25 hertz. So she goes back and forth 0.25 swings per second, or 0.25 hertz. And actually, it's a pretty basic formula what that frequency will be. I think it's 2 pi squared of L over G. So it depends on the length of the swing, and it depends on gravity, which doesn't change much on Earth. It doesn't depend on how big his daughter, Joe's daughter, granddaughter is. Doesn't depend on how much she weighs. It depends on how long that swing is. But that's for a swing. We're going to talk about spindles in a minute. So Joe's daughter goes back and forth at 0.25 hertz, or 1/4 of a cycle per second, or 4 seconds per cycle. And hopefully, if Joe knows what he's doing, he's going to push his granddaughter, every 4 seconds. He's not going to push every 2 seconds. He's not going to push every second. He's not going to push every 6 seconds. He's going to push her at just the right time every 4 seconds. And therefore, Joe's granddaughter is going to go higher and higher and higher. Okay. So he pushes every 4 seconds. Hopefully, if he knows what he's doing and he wants his daughter or granddaughter to go higher and higher. If Joe pushes every 3 seconds, or every 1 second, or every 5 seconds, his daughter is just not going to go very high because she's not being excited at the natural frequency of the spring. She's being excited or pushed at some other frequency. Now, how does this apply to grinding? Now, your grinding spindle likes to bounce up and down, and it likes to bounce up and down at some certain frequency. If this is your spindle and you pull on it, it's going to go boing, 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 boing. And that is about boing, 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 boing. It's about 3 boings per second, 3 hertz. In actuality, they really go boing, 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 boing. They go something like 400 bounces a second if you have a stiff spindle. If you don't have a stiff spindle, it might go 200 bounces a second, something like that. But that wheel wants to bounce up and down 300 times a second. Okay, if you have a stiffer spindle, it'll bounce up and down faster, sort of higher frequency. If you have an unstiff spindle, like an ID grinding wheel, it's going to bounce up and down at a low frequency. And you can do a bunch of calculations to sort of kind of estimate that, what that frequency is, based on a basic calculation. It gets a little more complicated because it's not just a mass on the end of a spring, but still you can get a ballpark number for what that frequency is, stiffness divided by mass. If you have a heavy aluminum, or if you have a heavy steel hub, if you have a steel hub super abrasive wheel, it's going to bounce up and down at a lower frequency than if you have an aluminum hub super abrasive wheel, which is going to bounce at a higher frequency, all things being equal. And we want things to bounce at a high frequency. Okay, so here we got a couple spindles. Stiff spindle going up and down 400 bounces a second. Not so stiff spindle going boing, 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 100 bounces a second. Super stiff spindle, maybe going at 800 bounces a second, especially if it's a very light wheel, not a heavy wheel. Something like that. Okay, now, what's it all mean? Okay, here's some ballpark numbers for natural frequencies that the spindle is going to bounce up and down at. So what does it all mean? What it means is you do not want to excite that system at the natural frequency. So let's take the second one. That guy likes to bounce up and down at 100 bounces a second. The worst thing you can do is rotate your wheel at 100 revolutions a second, because your wheel is not perfectly balanced. Even if you have an auto balancer, it's not perfectly balanced. And we do not want to excite that guy at 100 revolutions per second, which would be 6,000 RPM. So if we stick on a wheel any wheel because all wheels are unbalanced to some degree. All wheels are untrue. All wheels are imperfect. So the last thing we want to do in that second one is to spin that wheel at 100 revolutions a second or 6,000 revolutions a minute. If we got it at 90 revolutions a second, that'd be okay. 110 would be okay. 105 might be okay. But if we start getting around 99, 100, 101, that's where we have problems. Okay, now, this is a bigger problem in ID grinding because ID wheels tend to have much, much lower natural frequencies, number one. And then because they're typically smaller, we tend to rotate them at higher RPMs. If we do cylindrical ID grinding, our natural frequency is here, our RPM might be here, and boom, if they get pretty close, things are just going to start bouncing up and down out of control. If we have a cylindrical OD wheel, those typically are stiffer, so they might bounce up and down at 400 hertz, but we're only going to rotate them at 1800 RPM. What is that, 30 revolutions a second? We're not even close. So we're probably not going to rotate our OD wheel at 400, 500 revolutions a second. That would be quite an accomplishment and kind of dangerous. So this is less of an issue in cylindrical OD than it is in cylindrical ID. And it can be a big issue if you've got a really small cylindrical ID wheel and some kind of small bore, because then you're going to spin that guy at a higher RPM. Okay, now, what does it all mean? It means that you, as G.I. Joe said, being aware is half the battle, and be aware that you might be spinning that wheel at close to the natural frequency. Now, there is a sort of kind of test you can do. Old school machinists do this. Put your hand on top of the machine and spin the wheel, and then gradually increase your wheel RPM. You can program it in, you can use the little override dial, whatever. And then as the wheel goes faster, you're going to get more vibration. There's no way around that because out of balance varies as the square of the speed. So if you double the RPM, you've got 4 times the imbalance. So imbalance is going to get worse. But if there's a point where as you're increasing the RPM, things get really bad and then not so bad, and then start progressively getting worse, that could be a resonant frequency. Now, the other option is to bring in a vibrations expert or do some tests, but a quick on-the-fly test you can try is gradually increase your RPM. Your vibration is going to get worse. And if there's a point where it gets a lot worse, then not as bad, and then it continues on getting worse, that could be a resonant frequency. And that's cheaper than doing a bunch of accelerometer tests. Okay? So that was very, very quick. I realized that. We covered the fundamental concept of resonance. We covered excitation. We covered an actual test to do it. But still, it gives you a short introduction. And try it out. Probably you're not going to do it on a cylindrical OD grinder. Surface grinder, maybe, probably not. ID grinding, yes. Maybe a surface grinder if you've got some hydraulic pump running at the same RPM same frequency that your natural frequency is. That can be an issue, but then things start getting complicated. You start chasing things all over the place, and next it's 2 hours later and you're still chasing this vibration. So try it out on an ID wheel that's spinning fast, see what you get. And if it's obvious, you want to avoid that frequency, because that frequency is a natural frequency. That frequency is a resonance frequency, and that is definitely not the RPM you want to run your wheel at. This is Jeff Badger, the Grinding Doc, discussing the fundamentals of grinding.